In part A of 2000, they want to know if why essentially selenium has 6 stable isotopes. In terms of atomic structure, explain what these isotopes have in common and how they are different. So we, when we're doing this, we don't want to miss this. When they say you got to explain what they have in common and how they're different, you need to hit both parts of that. It's really easy to only talk about the different part, but they're implying that there's a grading point for each one of them, so let's make sure that we don't miss them. Now over here on the right, I've written 2 isotopes of selenium, and you remember that they have to have the same atomic number. They have to have the same number of protons. Where they different is in the mass number on top. So I don't know, let's say 64, and this one is 65. So in this one, we know that it would have 34 protons, but it would have 30 neutrons. We just subtract the 2 numbers and we can figure that out. Whereas this isotope would have 34 protons and 31 neutrons if we subtract those 2 numbers. So they are different in the number of neutrons, but they're the same in the number of protons. So here's what I've written. Isotopes of selenium have the same number of protons and have different number of neutrons and mass. It has to be mass. You probably don't have to say the mass part, but they do have to have different masses. And I think that's it. You notice the bullet point strategy works well here. It makes us sort of make sure that we hit the same and different, and we don't avoid answering that part of the question. Part B, write the complete electron configuration for a selenium atom in the ground state. The operable word here is complete. No abbreviations using noble gases. So let's start there. You notice I've numbered my periodic table columns, and selenium's right here. So we're essentially going to read the electron configuration off the periodic table. Remembering that these 2 columns are the S area up until this point right in here. We've got the D area. Over here we've got the P area, the entire block with exception to this, which is also an S. And then down here we have the F area, which we're not going to use. So the electron configuration starts at the beginning in column or row 1. This hydrogen is in the S area, and there is 2 blocks indicating 2 electrons. That's terrible too. And then we come down the second row. We're in the S area. There's 2 blocks there. We come across. Then we get to the 2p area over here, and there's 6 electrons. And then we get to the 3s area, and there's 2 electrons. Then we come across to the 3p, and there's 6 electrons. Then we come down to the 4s. There's 2 electrons. And lastly, we get over. Oh no, we still got to wait. Yeah, and then lastly we get to the D's, and remember we drop that down to 3d10, and then our last area is the P's, but we only have 4 P's, so 4p4. And then they say determine the number of unpaired electrons in the ground state and explain your reasoning. So the way I would do that is there's a couple different ways to do it, but you know that the unpaired electrons, if there are any, are going to be in that highest energy orbital. So I would draw out a p, and you remember that a p can hold up to 6 electrons, and so it's going to have 3 lines because there's 2 electrons per line. So this is a 4p orbital, and we're going to put 4 electrons in it. And so 1, 2, 3, 4. And you remember we were following Hund's rule by spreading them out first. So our answer is there are 2 unpaired electrons. And then we need to come up with a reason. And you notice that I'm running out of room here. But the rationale would be that this is what the highest energy orbital looks like. And because we follow Hund's rule, and I think it's going to be important to, maybe you don't have to say Hund's rule, but because there are equal energy level orbitals, the electrons spread out first. And so when you do that, you end up with 2 unpaired electrons. In the explanation, they're definitely looking for some understanding of Hund's rule. Part C1, so we want to know why selenium, which is right here, has a less ionization energy than that of bromine, which is right here. And actually I'm going to delete that if I can. No, I can't delete that. I'll erase it because you can't see the key and important thing there, which is we got to keep the, erase it again, and then we can go a little bit higher. There we go. So those are the two atoms that we're looking for. So why is it that selenium has a lower first ionization energy than bromine? Remember, our three choices are effective nuclear charge, shielding, or electron-electron repulsions. And hopefully by now you started to spot if they're in the same row, it's definitely going to be effective nuclear charge because bromine has 35 protons and selenium has 34. So I'm going to write the argument down. All right, so here's my argument. Selenium has less ionization energy than bromine because, boom, bromine has 35 protons, listing a specific number. Selenium has 34 protons. Then we notice we mentioned, by doing bullet points, we mentioned both elements. Therefore, the lower nuclear charge of the selenium atom will result in less Coulombic attractions with the valence electrons, requiring less energy to remove them. It's pretty short, it's brief, and it hits all the points that we need to hit. In C part 2, they want to know why selenium has greater ionization energy than tellurium. So those are the two elements we want. And it's definitely not going to be effective nuclear charge because they aren't in the same row. It's probably going to have a lot more to do with shielding. We could make a Coulombic attractions argument here, but let me write one down. Alright, now I was going to go back and erase some things about this, but I think some of the things that I did in here, the mistakes I made, can be instructive. So let's look at it. Selenium has greater first ionization energy than tellurium because, well, the first part's pretty good. You notice I mentioned both elements, and I mentioned something specific about their atomic structure. Selenium has 3 shells of core electrons, because you remember that the shells correspond to the rows. So 1, 2, 3, 4. So selenium has 4 shells, but it has 3 core shells. And so the same argument goes for tellurium has 4 shells of core electrons. So we're making a shielding argument. Therefore, the increased shielding experienced by the valence electrons of tellurium, because they have more shells, will result in less Coulombic attraction, making tellurium's electrons easier to remove. The argument's not bad, and I think it would get credit, but easier to remove, I wish I hadn't said it that way. That's kind of common language. What would be a better way to say that? Requiring less energy to remove, I think would be better, as opposed to using this sort of generic language. And then the other thing is, in general, the argument, while it's accurate, you notice, remember the way it was phrased, and I don't think they're going to be this picky, but it's possible. They said selenium is greater than tellurium. You notice they were talking about selenium, and I made my argument down here about tellurium, and you have to infer what it means for selenium from it. So I wish I had said the increased shielding experienced, or the decreased shielding experienced by selenium will result in more Coulombic attractions, making selenium's electrons more difficult to remove, or requiring more energy to remove. And it seems like a subtle thing, but it's a good idea to answer the question that they're actually asking. All right, and then finally D. Now D is more of a bonding question, and it won't be on Thursday's test. But we might as well look at it because that's what we're doing in our next unit. So selenium reacts with fluorine to make SeF4. Draw the complete Lewis electron dot structure for SeF4 and sketch the molecular structure. You notice that's kind of an interesting one. They want you to make somewhat of a sketch to represent it accurately. So let's see how we might do that. Well, first thing we got to do is we've got to add up the valence electrons. So you know selenium here has 1, 2, 3, 4, 5, 6 valence electrons. And fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. But there's 4 of them. So 7 times 4 is 28. And then we got to add our 28 to our 6. And we're going to get 34. And it looks like a reasonable number because you remember that's got to be even. So we're going to put selenium in the middle because it's the one there's least of. We're going to spread out our fluorines. And then we're going to start spreading around our electrons. Remember, we've already used 2, 4, 6, 8 just by doing the bonds. But we'll come back and count them at the end. Because remember, they all have to have 8 electrons around them. So I'm going to put 6 dots around each one, and the line indicates 2 more, so that's 8. There we go, almost done. Remember, AP wants you to darken them in pretty good, so they're sure they're dots. So I've used 8 around each one. 8 times 4 is 32, and that means I have 2 more left over to go on the central atom. And you remember, usually those we put a little orbital loop on to indicate that it's an orbital. All right, very good. Now they want us to draw a molecular structure, and what they're trying to get us to think about is they're trying to get us to think about shape. So you'll notice that we have 1, 2, 3, 4, 5 directions coming off of this. So our general shape is going to be, I'm going to draw it up here, is going to be sort of, this is the Mercedes star that's flat, and then head and feet like that. So it's trigonal pyramidal is its general shape, where this thing on top we're going to say is a lone pair. So I'm going to draw it over. Here's our SE. There's our lone pair. This is a fluorine. This is a fluorine. This is a fluorine. And this is a fluorine. So that might be a reasonable molecular structure. Then they say indicate whether the molecule is polar or nonpolar. I'm going to say that this molecule definitely is polar. And they want to know why. And you remember there are always 2 reasons. The reason it's polar is, 1, there is a polar bond. And our polar bond, by the way, is SEF. And the net dipoles, I'm going to say the dipoles. The dipoles do not cancel. Due to the asymmetrical shape. And it would be nice if we said what that shape was. And, you know, I think this is going to be one of these ones. I think this one is seesaw. I'm not going to be able to fit it on here, but saying what the shape is, being specific about that, being specific about what the bond is, and then I think that's good enough. I'm going to say polar because, and I think this actually would be an AP good enough argument. It doesn't have to be full sentences or anything like that.